Welcome to the video lecture for Force and Newton's Law of Motion for Unit 3. I'm going to start out with a base definition of force. It's a pretty simple one. A force is just a push or a pull. There are a lot of different ways that this can be accomplished, but basically that's it. The direction of that push or pull is really important to what a force is, though, and that means that this quantity is also a vector quantity, just like velocity and acceleration and displacement from before. We'll see it'll actually be in the same direction as an acceleration. Some examples would be things like gravity, friction. We can have an electrostatic force, like when you rub a balloon on your hair and stick it to a wall or ceiling. There are lots of, and any sort of push that you encounter. Force only comes in 4 different flavors, and every force that we experience is one of these 4 types. The first 2 are common every day that you are used to dealing with, namely gravitational. And for gravitational force, the thing that I want you to remember is that all objects in the universe attract one another. Anything with mass attracts one another. So you sitting in maybe in your home watching this, and me sitting in my home watching this, we're attracted together by a very small, but nonetheless present gravitational force, because we both have mass, and our masses would attract one another. Now that's really weak in comparison to something like the Earth attracting us, because its mass is huge. And so it's really not a measurable force even between us. But it is still there. The second type is an electromagnetic force. And this is anything with charge, like electrons or protons, will attract and repel each other. We're made up of atoms, which are also made up of electrons and protons. And this governs how we interact with almost everything around us. So, resting with my hands on my desk, my hands don't sink into my desk. That's because my hands, on the outer part of the atoms that make up my hands, are electrons. Same with my desk. And when the electrons of my hand get very close to the electrons in the desk, they repel each other very, very strongly. And so my atoms are not actually physically touching the atoms of the desk. Instead, the electrons in both are so close together that they apply a force between them, repelling each other. And we feel that because our nerves are set up to feel that force, to measure that force. But in actual fact, our atoms don't touch. The electrons from the 2 will bump into each other, and that's why when you pick up a pot from the stove, it will feel hot. The electrons in that pot are moving really, really fast, and they'll crash into some of the electrons in your hand and transfer some of that energy. So electrons can bump into each other, but the atoms of the pot, whether it's steel or copper, whichever the atoms are, don't actually hit the atoms, not nucleus to nucleus. Speaking of atoms, the last 2 types of forces only occur within atoms. First is a strong nuclear force. This one holds atoms together. If you think about this electromagnetic force, I said that we know that like charges repel. Well, inside a nucleus, you've got a whole bunch of positive charges in the form of protons, all stuck together in an extremely small space. If there wasn't something holding them together, all those positive protons would repel each other and no atom would ever be formed. So it's a very good thing that this does occur, because this is what allows atoms bigger than hydrogen, which is almost all of them, to even be formed. There is a limit to this, because there's also something called a weak nuclear force. And this is a force that actually helps to break atoms apart. So when you get a very big atom, things like plutonium or uranium, they're so big that this weak nuclear force is enough to tip the scales and break the atoms apart. This is responsible for radioactivity. So the first 2 you see all the time. Second 2 are really only in atomic nuclei. If there's one person that we can point to and say he's the most important person dealing with forces, that would be Sir Isaac Newton. He was an English scientist who lived from 1643 to 1727. Here's a portrait of him. Handsome looking guy, great hair. He did lots of things in science, and because of his contributions, he was knighted. That's why it's Sir Isaac Newton. He did telescopes, and he was also worked with prisms and was the first person to show that white light can be split into the rainbow of colors, and kind of explain then how rainbows are formed. He developed calculus, which is an extremely important branch of mathematics, especially in science. He actually developed this at the same time as another man named Leibniz. Newton got the credit initially because he published his work first, although nowadays we know Leibniz was at least as important in that, and developed it at the same time. For us, the most important things, at least in this class, were that he developed his law of universal gravitation, which is rule. It's a description of how objects with mass attract each other, so how much force is involved. And this is true between us and the Earth, or between the Earth and the Moon, or the Earth and the Sun. Anything with mass, that law tells us how much force is involved. For us, what we're going to focus on are his laws of motion, and there are 3 of them. The first deals with something called inertia, so it's often called the law of inertia. Inertia is the tendency of an object with mass to resist changes in motion. So if you give something a good shove, like let's say a car is rolling downhill, it's got some inertia, it's moving, and it's going to be really hard to stop that car. Likewise, if it's sitting on, if you've ever run out of gas and had to push a car, it's really hard to push because the car is so massive, it has lots of inertia. This law is usually summed up in the following statement. An object in motion will stay in uniform motion, and an object at rest will remain at rest unless acted upon by an unbalanced force. This means that if it's got a velocity, it will keep that velocity. Same speed, same distance. If it's at rest, it will remain at rest, unless it's got some force on it. In other words, if there's a change in velocity occurring, there must also be a net force. Net force here means a total force. So if forces are balanced on it, it's not going to change its velocity. It's only if they're unbalanced. Second law can be written in English as the acceleration of an object is proportional to the force acting on it and inversely proportional to its mass, but it's usually instead quoted as a formula. F equals m times a. The force is proportional to both the mass and the acceleration. This is how it's typically written. Not exactly how Newton wrote it, but for our purposes, it's certainly good enough. You'll notice that force and acceleration both have arrows over them, indicating that they are vectors. Their directions are exactly the same as one another. F is our force. We always measured in newtons, named after Sir Isaac Newton. M is our mass, and we don't use the base units for this because kilograms are much more convenient to measure a lot of things in. So we use kilograms for any of the calculations in here. So if you get a mass in grams, you need to first convert it to kilograms before making this force calculation. And lastly, A is our acceleration from, just like last chapter, it's measured in meters per second squared, or meters per second if you prefer. Now we've got a few examples. First off is a 2010 Corvette, which is the ZR1 model. It's got a 6.2 liter engine. It's got a mass of 1,515 kilograms, and when it goes from 0 to 60, if you really stomp on it, it's got an acceleration of 7.9 meters per second squared. So we want to say how much force then is applied by this engine to the road to get the car going. We know a formula for force from Newton's second law. F equals m times a. We want to find F. So we need to define mass, m, and we're given that. It's 15 kilograms. And we're given the acceleration, 7.9 meters per second squared. So all we have to do, multiply these two together. 15 kilograms times 7.9 meters per second squared. gives us a total of force of 11,968.5. Now the units here, we actually do a shorthand. The units of a force are newtons. And we get a newton by multiplying kilograms times meters per second squared. So a handy thing to remember is that 1 newton is equal to 1 kilogram meter per second squared. We'll use this when we rearrange the formulas, especially because we won't always be looking for force, obviously. Sometimes you'll be given a force and then find something else. Case in point, let's take that Corvette engine and we're just going to round it to 12,000 newtons. We're going to put it in a smart car which has a mass of only 730 kilograms. We want to find the acceleration. Well, once again, we know the relationship amongst those. Force is equal to mass times acceleration. This time we want to find acceleration. So we needed to find the force, which was given 12,000 newtons, and the mass, which in this smart car is just 730 kilograms. And we want to solve for acceleration. So we have to rearrange our formula over here. To do that, I need to get rid of that m. So I'm going to divide both sides by the mass. Masses cancel, leaving just acceleration there. And it shows that acceleration is our force over our mass. Well, we know the force we said was 12,000 newtons over our mass of just 730 kilograms now. So dividing those out, we get 16.4. Now the units here, this is why it's important to remember what a newton means. A newton is a kilogram meter per second squared divided by kilograms. So here, the kilogram part will cancel with kilograms on top, leaving for us just meters per second squared, which is a very good unit for acceleration. So that gives us confidence that we did it right because we came up with the units that we should expect. Here's a review question. How long would it take, same souped up smart car, to go from 0 to 60 miles per hour, which is 0 to 26.8 meters per second? Well, we want to find a time. How long means what is time. We're also given two velocities. We are given a 0 and 26.8 meters per second. And since we're starting at 0, we know that's an initial velocity. We know that we're ending up at 26.8, so that's a final velocity. And from the last problem, we know that the acceleration is about 16.4 meters per second squared. So going back to last chapter, we know that acceleration is the change in velocity, v final minus v initial, over time. I need to solve for that time. And so I need to get this time on the top of the equation and alone. So I'm going to multiply both sides by time to do that. This t with that t will cancel. And that gives me t times a equal to bf minus di. Then I need to get rid of the acceleration there, so I'm going to divide both sides by a. These two cancel, leaving me time is equal to velocity final minus velocity initial over acceleration. And putting values in for that, I know final velocity is 26.8 meters per second minus initial is 0 meters per second, so that doesn't affect us at all. Divided by our acceleration of 16.4 meters per second squared. Obviously this one's nothing, so we just need to take 26.8 meters per second divided by 16.4 meters per second squared. Gives us 1.63. Now the units here, remember, use your math background, you're dividing fractions, meters per second over meters per second squared. You keep the first one, so it's meters per second. Flip, or change this from a divided by to multiplied by, and then flip the bottom, seconds squared over meters. That means we got a meter on top, meter on the bottom. We got seconds on the bottom, and that takes one of those seconds on top, leaving us with just units of seconds, which makes perfect sense for a tie. Next, we've got a special case of the second law, which is how do we calculate weight? First off, what is weight? Weight is the force of gravity that acts on something. We already know how to calculate a force. It's mass times acceleration. But this is a special acceleration. It's the acceleration of gravity, which we also know is g. So we rewrite that formula that we had, F equals ma, to account for this. I've used a little subscript g here to show that this is the force of gravity. I don't want to use W for weight because we're going to use W for work next chapter, and that could get very quickly confusing. And instead of our just generic acceleration, we know the acceleration. It's actually negative 9.8 meters per second squared. Usually, we're going to forget about this negative because we know weight is always going down towards the center of the earth. So it's just a little shorthand. So let's take an example. Mr. Splenica has a mass of 70 kilograms. That's actually not accurate. 67 kilograms. We want to calculate what my weight is. Well, we know the formula. It's right above us, so we have to define what the mass is. That's obvious, 67 kilograms. Remember, this has to be in kilograms, not grams. And G is going to be 9.8 meters per second squared. It is negative, but again, for this problem, we don't have to worry too much about it. Force of gravity then acting on me, my weight, 67 kilograms times 9.8 meters per second squared. Gives me 656.6 newtons. And weight is measured in newtons here, just like any other force, because it is a force. Okay, the third law, another one that you're familiar with. It's typically stated for every action there is an equal and opposite reaction. That means if I push on something, whether it moves or not, the force it pushes back on me with is the same as what I push it on. So even if it's moving, if I push my chair around my room, I might be applying 50 newtons to it. It's applying 50 newtons back to me. Now there are other interactions. The floor is interacting with the chair, and the force between the floor and the chair is the same either way as well. Now since I'm pushing it, that also means that the floor is applying less force on the chair than I am. But those individual interactions, the forces will be the same. To illustrate this, let's meet George, who's a bully, and he's after milk money from little Eddie. George pushes Eddie with 300 newtons of force. Now normally you'd think that, well, he's a bully, he's going to get in trouble, right? But George has been paying attention in science class, and he explains that according to Newton's third law, Eddie pushed him with exactly the same amount of force. Teacher's hands are tied because he's right. Don't worry too much about Eddie, though. He's got a plan and some exploding pocket change. Okay, this concludes our lecture on the 3 laws of motion. I hope you've enjoyed it as much as I have.